In this example, the function we're going to graph is e to the x over x squared. Let's see if we can see that pretty well. Okay, so immediately the first thing is domain. You can see a 0 in the bottom is going to be bad. E to the x is defined everywhere. So really our domain is everything except x equals 0. So like that. Now, intercepts and asymptotes, this is an interesting question. Clearly we can see there's going to be a vertical asymptote at x equals 0, right? Because if I take the limit as x goes to 0, in fact, let me just do this for a minute. I'll go from the right? This is going to be 1 over 0, so this goes this way. So basically, this is going to be infinity. And it's, in fact, going to be plus infinity from both sides because if it's x squared in the bottom. So even if I go from the left, this is still positive, and this is still positive. So basically, we have a vertical asymptote at x equals 0, right? Where the function is going to positive infinity on both sides. So let me write that somewhere because I'm going to need it, right? X of f of x is infinity. Useful information there. So that's for our vertical asymptote. Now, the other question, though, well, the question of intercepts, we can see there's not going to be any intercepts because, of course, 0 isn't in the domain. E to the x is never 0 anyway, so no intercepts at all. Now, the other question, though, when it says asymptotes, it's talking about not just vertical asymptotes, but horizontal asymptotes. And we know e to the x has a horizontal asymptote when x is negative. So we got to kind of look at this situation. So let's see. If I do the limit as x goes to infinity of e to the x over x squared, this is a situation, right? That e to the x is going to infinity, and x squared is also going to infinity. So this is a classic L'Hopital's rule issue because I've got infinity over infinity going on here, right? So using L'Hopital's rule, I take the derivative of the top, divide by the derivative of the bottom. I still have infinity over infinity. So I have to do it again. So second time L'Hopital's rule, I am at e to the x over 2. All right. Well, what am I supposed to do with that? Now I can see, though, now it's infinity over 2, right? Because the bottom is just 2. This top is going to infinity as x goes to infinity. So on the right-hand side, we do not have any horizontal asymptote. So let me just write this here because this n-term behavior is going to be helpful for us as well. But on the left-hand side, when x goes to negative infinity, look what happens, right? Because this is infinity in the bottom, fine, but this is going to 0 on top. So I can really think about this as being 0 over infinity, or 0 times 0, right? Because 1 over infinity is going to be 0, right? So this is just going to go to 0. So I do have a horizontal asymptote on the left, but only on the left, not on the right. And that's because it's e to the x. Horizontal asymptote, y equals 0 on left. Okay. So we got that. So we did have to use L'Hopital's rule to figure out that the one side goes off to infinity, but the other side just sort of automatically ends up going to 0. Now I need to take derivatives. So it's up to you if you want to use the quotient rule or if you want to write it as x to the minus 2 e to the x and use the product rule. I'm going to do the quotient rule. So I have x squared times the derivative of e to the x, which is e to the x, minus e to the x times the derivative of x squared, which is 2x. Okay, so I can pull an x out of the x e to the x out of the top, right? And then I have x minus 2. This is over x to the fourth. So eventually I get e to the x times x minus 2 over x cubed. So that's my first derivative. Well, what do I want to know? I need to know the critical points, so I need to know where this is not defined and where it's 0. Obviously, it's not defined at x equals 0, right? And it's equal to 0 at x equals 2, right? So let me write that a little bit more carefully. The derivative is equal to 0 when my top is equal to 0. So it's e to the x times x minus 2 equals 0. E to the x, though, is never equal to 0. So that just leaves x minus 2 equal to 0 or x equals 2. Okay? That gives me, I'm really going to run out of space here, I know it. We'll make the graph small. That gives me the following thing. For my sign chart for the first derivative, I have those 2 points, 0 and 2. So let's look at this. So if I'm on the left-hand side of 0, my top's going to be 0 and my top's going to be negative and my bottom's going to be negative, right? So I'm going to end up with a positive value. If I put in, for example, x equals negative 1, right? This guy is always positive, so it doesn't make a difference, but I would have minus 3 over minus 1. If I put in something between 0 and 2, on the other hand, this is always positive, this is always positive, this one's going to be negative. So if I check it x equals 1, I'm going to get a negative e. And then if I look for numbers that are bigger than 2, everything is going to be positive, so that's going to be like this. Now, let's be careful here. This is, as we know, already we know that's a vertical asymptote. So this implies, if I'm going to look at 2, that 2 is perfectly fine here. It's 0 there. So that's going to be a minimum. Okay? So my increasing, it's going to be increasing from negative infinity to 0 and from 2 to infinity. And it's going to be decreasing from 0 to 2. It looks like I have no local max. And my minimum is at 2. So if I figure out what that is, f of 2 is e squared over 4. When I draw it, I'll figure out what that number is. But I want the exact value, right? E squared over 4 is going to be the point which gives us the minimum. All right. If I have then f prime of x, x e to the x minus 2 e to the x over x cubed. And now I'm going to take the derivative here. Because I need the second derivative, I need to know about the concavity. So second derivative, x to the 6th, right? X cubed squared. And then I'm going to have x cubed times the derivative of the top. Maybe I should have just written it like this. What do you think? It'd be a little bit easier to do, right? Because then I'm going to have x minus 2 times e to the x, that times the derivative of that, plus that times the derivative of that, which is just going to be e to the x, right? And then subtract this times the derivative of that. Here. I'm going to erase it later so that I keep this. But I have x minus 2 e to the x times the derivative of the bottom, which is 3x squared. So sorry for the bad board work there. If I'm going to work this out a little bit, this would be x cubed times x e to the x minus e to the x, because I've got minus 2 e to the x plus 1 e to the x, minus 3x squared times x e to the x minus 2 e to the x. All right, so everything has an e to the x and an x squared in it. So let's see what I can do here. I'm going to pull out the x squared e to the x. This would be x to the fourth, or x squared minus x minus 3x e to the x plus 6 is what I got. All right. All right. Except no e to the x here. I pulled out the e to the x. So that's not right. Okay, let's look at this again. This is what I get for doing too many things at once, right? So this is x to the fourth e to the x. That's this. This is x cubed e to the x. That's this. This is 3x cubed e to the x. That's that. And this is, yes, plus 6. Okay. So this one cancels with that. There's going to be a 4 in the bottom. So eventually I have e to the x over x to the fourth. And then I have this thing, which is x squared minus 4x plus 6. Okay. So what about this x squared minus 4x plus 6? So we need to figure out, again, the critical points of this guy are going to be where that top is 0, and what about the bottom, right? So let's check about this top business first. Let me make sure that my signs are right. So the top is going to be a quadratic, and it doesn't obviously factor nicely, right? So if I've got x, if I'm going to set this quadratic equal to 0, it's going to be minus b plus minus the square root of b squared, which would be 16, minus 4ac, 24. Okay, this has no real roots. All right, that's fine. And so it's just kind of what I expected. But so this top is never 0, and the bottom is only 0 at 0. So the only place where this thing can change concavity is at x equals 0. Okay, so let us make our sign chart for the second derivative. This is, of course, where we have our asymptote. But now if we look at this, we can see, because this is never equal to 0, right? It's always going to be positive. So this top is positive, this is positive, this is positive. This thing is positive everywhere, except for at 0 where it doesn't exist. So this is always concave up. So concave up from negative infinity to 0, and from 0 to infinity, no points of inflection. All right. So let's erase this stuff. And sort of see what we've got here. This is a graph which doesn't have a whole lot of points to put on, right? So here's my axes. I know that from what I got here, I have a vertical asymptote at x equals 0. On the left-hand side, I have a horizontal asymptote at y equals 0. And on this left-hand side of 0, the function is always increasing and always concave up. So this has just got to do this. I mean, there's nothing else it's going to do, right? It's always increasing, it's always concave up, and it's shaped by those asymptotes. There's no other points. Now, on the right-hand side of 0, at least this happens, but then it makes sense that there would be a dip here and go up because the whole thing is concave up. So let me put my minimum point. It was at 2, and this e squared over 4, it turns out, I wrote this down, 1.85, something like this. So it's about here. And I am going here to positive infinity on both sides here. So I'm going up, I'm down there, and then I go out kind of more or less however that is. So you end up with a kind of this maybe a little bit rounder than I made it. Whatever. A little bit rounder, it goes up fast, right? Because it's going to go up like e to the x, not quite as fast because you're dividing by x squared, but eventually it's still going to go off to infinity. So there's that.